Hi guys, in this lecture we will be starting with the concept of two-port networks. But before studying two-port networks, first we must get a grasp of the term port. What is meant by port? It is basically a pair of terminals from which a current can enter or leave a network. Okay? Like suppose if I tell you, let me take the case of a transformer. Okay? So current I1 will enter here, I2 will leave here. So these two terminals A and B, they will constitute a port. Let us say port 1, this is port 2, the terminals C and D. I1 will be traveling like this and I2 will be traveling like this. Okay. So net current entering or leaving a port is 0. I1 is entering from A, I1 is leaving from B. Because current needs a closed loop path for its flow, so the net current entering or leaving will be 0. So that is how a port is defined. It is a pair of terminals from which a current may enter or leave a network. Okay. Now, why these two-port networks are necessary for us? Basically, two-port networks is a way of modeling any system. Okay. In two-port networks, what we do is usually we model in terms of parameters. Okay. These parameters are independent of how the circuit works. That is, it is just a black box representation of a system in which you know the relationship between the parameters on one side and the parameters on the other side. Like voltage and current of one port will be related to the voltage and current of the other port, but you do not know internally how the system is constituted. Okay. But we will be able to determine the voltage and current of the system by the use of these parameters. That is the beauty of two-port parameter. Okay. So that means even if you are modeling a transmission line, a transformer, a BJT or FET, you do not care about the device or you do not care about the machine. You just care about what is the relationship between parameters on one side and the parameters on other side. Okay. So basically two-port networks are used to model BJT, op-amp, and in electrical it will be used to model transformer, transmission lines. Okay. So it can be used to model a wide variety of systems provided that they have two ports, one for the input and other for the output. Okay. Like in transformer, primary is used as the input port, secondary is used as the output port. Like in case of BJT, base emitter junction is used as the input port, collector emitter junction is used as the output port in common emitter configuration. Now, similarly, one-port networks can also be defined. In one-port network, we just have one port, either for the that is used for the input. Okay, like here, if you see V1 I1, this is acting as one port. V2 I2 is the other port. Okay, so that is for one network, and this is for the other network. So based on this, we define certain parameters. First one is your Z11, that is V1 by I1. It is known as driving point impedance. Okay. And since it is at the input port, it is known as driving point input impedance. Similarly, the reciprocal of this will be admittance. So it will be driving point input admittance. If we take the case of other network here, Z22 will be V2 by I2, that is driving point output impedance. What about Y22? That is I2 upon V2. It is driving point output admittance. So these parameters are usually defined for the case of one port network, as we do not have any transfer parameters. What is meant by transfer parameters? The parameters that relate to current on one side and voltage of the other side, or even current on one side to the current of the other side. That is, transfer parameters will relate one parameter on one side and the other parameter on the other side. These parameters that we have defined, driving point, impedance and admittance, they relate only the one-sided parameters, that is voltage and current on one side or the voltage and current on the other side. Okay, they do not interrelate the parameters on both sides of the network, but both sided parameters can only be defined for the two-port network, because you at least need two ports to define the transfer parameters. Now when it comes to two-port networks, two terms we commonly use: symmetrical and reciprocal. Now what is meant by symmetrical and reciprocal? Like a two-port network will be represented something like this. This is my network. This is V1 and the current entering will be I1. Similarly, this is V2. Current entering is I2. Now if you look from this side, that is from port 1, and you look from the other side, that is from port 2, if network is identical from both the sides, it is known as symmetrical. Means network identical from both ends. Okay, that is the condition for symmetrical network. How you can also explain it is, if the driving point impedance is same from both the sides, that is, I can say that if Z11 equal to Z22, then also I can say that the network is symmetrical. The next term is reciprocal. With respect to reciprocal, we have studied one network theorem that is known as reciprocity theorem. What was reciprocity theorem? Here we stated that if we interchange the terminals of response and excitation, then also the ratio of response to excitation remains the same. Okay. Interchange terminals, but yet response is same, or we can say response by excitation. So that is what is your reciprocal network. Now most practical networks should be reciprocal. Like in case of physical parameters, like suppose we are talking about transmission line. Then what is a transmission line? It is just a power carrier that is connected between the two nodes. It has the sole function of carrying the current from one end to the other end. But while connecting a transmission line, you do not know which end to connect to the source and which end to connect to the load. That is, even if you interchange the ends, it still has to carry the same current. That is why transmission line will be reciprocal always. Okay. So that is how in case of practical systems they must be reciprocal if they have symmetrical construction from the sending and the receiving end, or from the input and the output ports. Now let us understand some parameters that are defined for the case of two-port network. Okay. First, let me show you an example of symmetrical network. Suppose we take a T circuit like this. 1, 1, let us say 2. Now if you look from this side, 1 ohm is the nearest, then 2 ohm, then 1 ohm. Even if you look from this side, 1 ohm is the nearest, 2 ohm, then 1 ohm. So that is your symmetrical network. But now suppose I change this value to, let us say, 5 ohm. Then if you see from this side, 5 ohm is coming first, then 2, then 1. If you see from this side, 1, 2, then 5. So it is not symmetrical now. Okay. Now it will be asymmetrical. So that is how even by direct observation I can identify the symmetry in a network. Or you can understand in this way, if you divide this network symmetrically, then both the ends must be mirror images of each other. But here there is 1 ohm resistor, here it is 5 ohm, so these are not mirror images, hence this is not a symmetrical network. Okay. So the first set of parameters that are defined for a two-port network is Z parameters. These are also known as open circuit parameters. That I'll tell you why these are known as open circuit parameters. Now, what does Z parameters do? They relate the voltages at both ends to the current at both ends. That is, it is a relation between the port voltages and the port currents. So how the relationship is defined? It is defined by means of superposition theorem. What we do is, we energize one port and then find out the voltage of both the ports, and then we energize other port and find out voltages again. The net voltage at any port will be equal to sum of the voltages due to I1 and I2. I1 is the current of port 1, I2 is the current of port 2. That is why it can be expressed as V1 is equal to Z11 I1, Z12 I2. This is the component of V1 due to I1, component of V1 due to I2. Similarly, V2, Z21 I1 plus Z22 I2. Component of V2 due to I1, component of V2 due to I2. In matrix form, we will express it as V1 V2 is equal to Z11, Z12, Z21, Z22, I1, I2. Okay. Usually the parameters of two-port network are used in matrix form because it is easier for us to operate in matrix form. There we can deal with a lot of parameters simultaneously. Now if you want to determine these parameters, like if I want to calculate Z11 from this equation, then I have to equate I2 equal to 0 so that the second term vanishes. So Z11 can be written as V1 by I1, V1 by I1 when I2 equal to 0. So what will you call Z11? Z11 will be called as open circuit input impedance. Why open circuit? Because when you are equating I2 equal to 0, you are essentially open circuiting the port number 2. Similarly, if you wish to calculate Z22, then we can calculate Z22 by means of second equation, which is V2 by I2 provided I1 equal to 0. So that will be called as open circuit output impedance. Here we are open circuiting the input port and then we are determining the output impedance. What about Z12? Z12 will be V1 by I2 provided I1 equal to 0. It will be called as open circuit transfer impedance. Open circuit transfer impedance at input. Okay. What about Z21? Z21 will be similarly V2 by I1 provided I2 equal to 0. That is your open circuit transfer impedance at output port. Okay. So that is why these are called as open circuit parameters, because if you wish to determine any parameter, then you have to equate one current to 0 or you have to make one port as open circuited. Out of two ports at any time, one port will be open to determine any parameter. Now as I told you, for the symmetry, what will be the condition? Driving point impedance from both ends must be same. That is Z11 equal to Z22 for symmetry. What about reciprocity? I told you the ratio of response to excitation must remain same. That is why Z12 should be equal to Z21 for reciprocity. Like even if you see here, Z12 is ratio of what? V1 by I2. That is, we have applied excitation I2 and we are obtaining the response V1. What is Z21? We have applied excitation at port 1 and observing the voltage at port 2. If both are the same, because the ratio of response to excitation must remain same, if we interchange the terminals or the ports, then only the network is reciprocal. So this is the condition for reciprocity, that Z12 should be equal to Z21. Similarly, we define Y parameters. Basically, these are the inverse of Z parameters. They will relate at the current at both the ports to the voltages at the ports. That is, I1 can be expressed as linear combination of V1 and V2. Similarly, I2 can also be expressed as linear combination of V1 and V2. So, again by superposition theorem, what we will do is, we will calculate I1 due to V1, then I1 due to V2, and we will add these components. Similarly for the case of I2. Now these are also known as short circuit parameters. As you might already have guessed it, like in the Z parameters, we were determining the parameters by open circuiting the ports. Here we will determine the parameters by short circuiting the ports. Now, here the equations that relate the current of one port to the voltage of the ports, I1 will be written as Y11 V1, Y12 V2. Similarly, I2 Y21 V1, Y22 V2. In matrix form, it can be written as I1, I2 will be equal to Y11, Y12, Y21, Y22, V1, V2. Okay. So that is how the Y parameters relate the current at both the ports to the voltages at the ports. Now to determine these parameters, Y11 can be written as I1 by V1 when V2 equal to 0. If you are equating any voltage equal to 0, that means you are short circuiting that port. So it will be known as short circuit input admittance. Similarly, Y22 will be I2 by V2 provided that V1 equal to 0. That is short circuit output admittance. Okay. These admittances will also be known as the driving point admittance. But when you want to define the relationship between current at one port and voltage at the other port, then you will define the transfer admittance. That is, if I write down Y12, it will be I1 by V2 provided V1 equal to 0. This will be transfer admittance short circuit transfer admittance at port 1. What about Y21? I2 by V1 provided V2 equal to 0. That is short circuit transfer admittance at port number 2. Okay. So that is how we define the impedance network, or we call it as impedance parameter and the admittance parameter. So what will be the condition for symmetry and reciprocity here? It will be similar to the Z parameters, what I'll say is y11 equal to y22 for the case of symmetry. Driving point admittance must be same, and y12 should be equal to y21 for reciprocity, because again we must keep the ratio of excitation to response or response to excitation same at both the terminals. And if you see, basically how the Z parameters were defined, V1 V2 is equal to Z parameters I1 I2. If we take the inverse of Z on both sides, Z inverse V1 V2 equal to I1 I2. That is, Y parameters are actually inverse of the Z parameters. Okay. So, to obtain the admittance parameter, you cannot directly take the reciprocal of the impedance parameters. Rather, you have to invert the matrix of the Z parameter. Do not think that y11 is equal to 1 upon z11. Rather, you have to take the inverse. The next set of parameters is known as H parameters or hybrid parameters. Now, the Z and Y parameters do not always exist. So, we have to define something called as hybrid parameter. Here, we are not relating the voltages to currents. Rather, voltage of one port will be expressed as function of the two parameters and current of the other port. Okay. That is, you choose voltage of one port and current of the other port. Like, V1 will be expressed as H11 I1, H12 V2, and I2 will be expressed as H21 I1 plus H22 V2. So, if you see voltage of port number 1 and current of port number 2, that is, it is mix of the impedance and the admittance parameter, hence it is known as hybrid parameters. In matrix form, it can be expressed as V1 I2 is equal to H11 H12 H21 H22 V2 I1 V2. Okay. Now, if you wish to find H11, H11 will be equal to V1 by I1, but when V2 equal to 0. So, it is driving point impedance under short circuit. So, it will be known as short circuit input impedance. What about H12? It is V1 by V2 provided I1 equal to 0. Now, usually how do you define the gain? We define the gain as the ratio of output to input, but it is the ratio of input upon output. So, it is your reverse voltage gain. So, it is your open circuit reverse voltage gain. What about H21? It is I2 by I1 when V2 equal to 0. So, that is your short circuit current gain, because it is the ratio of output current to the input current. Okay, or even you can call it as short circuit forward current gain to distinguish it from the reverse current gain or reverse voltage gain. We can call it as forward. What about H22? It will be I2 by V2 provided I1 equal to 0. So, that is equal to open circuit output admittance, because equating I1 equal to 0, we are open circuiting the input port and then we are calculating the admittance at the output port. So, it will be called as open circuit output admittance. Now, the conditions for symmetry and reciprocity for these parameters For symmetry, what will be the condition? The condition will be mod of h parameter must be equal to 1. That is mod h11, h12, h21, h22 must be equal to 1, due to which it will be h11, h22 minus h12, h21 will be equal to 1. Why is it the condition for symmetry? So that if you want to find out like here we are determining V1 I2, sorry, I1 V2. So that if you change the parameters to I1 V2 in terms of V1 I2, the inverse will not have any effect, because inverse is nothing but adjoint divided by the determinant. If determinant is 1, the magnitudes of the parameters will remain same. Okay. What about for reciprocity? For reciprocity, the condition is h12 is equal to minus h21. Okay. Because here what happens is we are assuming both the parameters of both the current set as inputs. Okay. That is I1 is also entering, I2 is also entering. But actually when it comes to a practical network, current must enter at one port and leave at the other port. That is why we have to introduce a negative sign in order to define the reciprocity. Reciprocity is nothing but if you interchange the response and the excitation, then their ratio must remain same. But as you can see here, current at both the terminals are entering. So you have to multiply one current by a minus sign in order to make that current leaving. Okay. Now as y parameters were defined as the inverse of z parameters, similarly g parameters are defined as inverse of h parameters. So these are also known as inverse hybrid parameters. So here what parameters we will relate? I1 and V2 will be related to V1 and I2. I1 will be G11 V1, G12 I2. V2 will be G21 V1, G22 I2. That means I1 V2 will be equal to G11 G12, G21 G22, V1 I2. Okay. Now if you wish to find G11, what you will do is I1 upon V1 given that I2 equal to 0. So it is your open circuit input admittance. Okay, we are open circuiting the port number 2 and determining the admittance at port 1. What about G12? It will be I1 by I2 provided V1 equal to 0. It is short circuit reverse current gain, because again the gain must be defined from output upon input. But here we are taking input current upon output current, hence the reverse gain. The next parameter will be G21, that is equal to how G21 will be defined? V2 by V1 given that I2 equal to 0. So what it will be? It will be equal to open circuit forward voltage gain, because it is taking the voltage at the output port upon voltage at the input port. What about G22? It will be V2 upon I1, sorry, V2 upon I2 provided V1 equal to 0. That means short circuit output impedance. Because by equating V1 equal to 0, we are short circuiting the port number 1 and determining the V2 by I2, that is the output impedance. Similar to hybrid parameters, what will be the condition for symmetry and reciprocity? For symmetry, we will say mod G equal to 1, that is G11 G22 minus G12 G21 must be equal to 1. And for reciprocity, G12 equal to minus G21. So remember, the conditions for symmetry and reciprocity remain the same in case of inverse parameter. That's why in case of Z and Y parameters, these conditions were same. In case of H and G parameters, again these conditions are same. Next we define the transmission parameters. Okay. Now these parameters are most important when we come to transmission lines or cables. Okay. Because usually these parameters are important when we cascade two systems. Cascade means when output of one system acts as the input of the other system. Then these parameters are especially helpful, and usually in case of transmission lines to achieve higher lengths or to achieve larger lengths of the line, because a transmission line is usually laid down for 200-300 km. That cannot be a single wire. It has to be a cascaded connection of multiple lines. In that case, we have to define the transmission parameters. How transmission parameters are defined? V1 equal to A V2 minus B I2. I1 equal to C V2 minus D I2. That is, they are relating the parameters of port number 1 to the parameters of port number 2. Why minus sign is introduced here? You can either introduce a minus sign or you can express a network like this, A, B, C, D, then show I2 like this. Because when I drew the two-port network, I had drawn something like this. It was the network, I1 was like this and I2 was like this. But actually current must enter from one port and leave from the other. So if you assume I2 as leaving, then no need of this minus sign, you will use a plus sign. But if you are assuming I2 as entering, then we have to show this negative sign. This negative sign just signifies that the current is leaving from the port number 2. So these can be expressed in matrix form as V1 I1 equal to A, B, C, D, V2 and minus I2. Okay. Minus I2 means current leaving from port number 2. Now if you want to find A, it will be V1 by V2 given that I2 equal to 0. That is open circuit reverse voltage gain. Why reverse gain? Because it is input voltage by output voltage. Or it can also be said that open circuit voltage ratio, because it is the ratio of two voltages. Then B, it will be equal to V1 by minus I2 provided that V2 equal to 0. So it is your short circuit transfer impedance. Why transfer impedance? Because voltage of one port and current of the other port. Why short circuit? Because V2 is 0. What about the parameter C? C can be written as I1 by V2 given that minus I2 equal to 0. That is equal to open circuit transfer admittance. Okay, because we are open circuiting the port number 2 and then we are finding the transfer admittance, that is I1 by V2. What about D? I1 by minus I2 provided that V2 equal to 0. That is short circuit current ratio or short circuit reverse current gain. Okay. Now, the condition for symmetry and reciprocity for these parameters is, for symmetry, A is equal to D. For reciprocity, mod T equal to 1, that is mod of ABCD equal to 1, that is AD minus BC equal to 1. This is the condition for the case of reciprocal network. Next, we define the transfer ratio. Okay. Now, the transfer ratio, the transfer voltage ratio. First of all, transfer voltage ratio, it is defined as G12 equal to V1 by V2 and G21 will be equal to V2 by V1. What about transfer current ratio? In transfer current ratio, it is defined as alpha. Alpha 12 is I1 by I2. Alpha 21 is I2 by I1. Okay. That is your transfer ratios for the voltages and current. Okay. Now, there are certain properties of the impedance parameters or impedance function and the transfer function, which you must always remember. For impedance function, that too we are talking about driving point. That is V1 upon I1 or V2 by I2. Here it is your minimum phase function. What is minimum phase function? All poles and zeros are in left half plane. When all poles and zeros lie in the left half plane, it is known as minimum phase function. Similarly, for the case of transfer function, poles must lie in the left half plane because it must be stable. Zeros can be right half as well as left half. But for driving point impedance function, all poles as well as zeros must lie in the left half plane. Okay. Now, as I told you, we define the hybrid and the inverse hybrid parameters where Z and Y parameters cannot be defined. Such is the case for the case of transformer. Why the Z and the Y parameters cannot be defined? Because the primary and the secondary are not directly connected to each other. They are isolated from each other. So we cannot define the Z and the Y parameters. There is no direct relationship between V1 and I2 or V2 and I2. Okay, that is the voltages cannot be expressed as functions of I1 and I2. Okay. That is why usually the transformer is modeled in terms of transmission parameters instead of your Z and the Y parameters. So let us summarize what we covered in this lecture. I told you what is meant by two-port network. Then we saw the Z parameters. V1, V2 is equal to Z11, Z12, Z21, Z22, I1, I2. Here for symmetry we define Z11 equal to Z22. For reciprocity we define Z12 equal to Z21. Inverse of these parameters were the Y parameters. I1, I2 equal to Y11, Y12, Y21, Y22, V1, V2. Again for symmetry we defined Y11 equal to Y22. For reciprocity Y12 equal to Y21. Then we looked at hybrid parameters which related the voltage at one port, that is V1 with I2. V1 and I2 with respect to I1 and V2. The parameters were H11, H12, H21, H22. Here for symmetry what we studied? For symmetry it was the case that mod of these parameters must be 1. H11 H11 H22 minus H21 H12 must be 1. And for reciprocity, H12 is equal to minus H21. What about inverse hybrid parameters? They were defined like V1, I2, G11, G12, G21, G22. Now these parameters will be something like, condition will be same as hybrid parameters and G12 equal to minus G21. And the last we studied about the ABCD parameters or the transmission parameters, that is V1 I1 equal to ABCD V2 minus I2. So the condition for symmetry was A equal to D. For reciprocity, AD minus BC equal to 1. So these are the parameters that are defined for the two-port network. In the next lecture, what we'll do is, we will look at some problems that have been based on these parameters.